Okay, so we're going to start with our position versus time graph, and we have the position on the y-axis in meters and the time on the x-axis in seconds. And our Mousetrap car went a total of 1.6 meters in 3.2 seconds. And this graph begins on the origin or at 0 because when you started the car, it was at 0, which is like the distance. It hadn't gone anywhere. And it increases because as the car moves, it's obviously going further in distance in the position as the position is furthering as time goes on. Now we're going to talk about our velocity versus time graph, and we have velocity on the y-axis in meters per second and time in seconds on the x-axis again. And to solve for velocity, we did delta x equals 1/2 delta t delta v. So we just plugged in our numbers that we already knew we had, or values, and in the equation, and we got our velocity equals 1. And this also begins at 0 because the car doesn't have any velocity when it starts, but it begins to move with positive increasing velocity, and then it reaches a peak and begins to slow down and is still moving with positive velocity but decreasing in speed. And so lastly, we're going to talk about the acceleration time graph, which is we again have time on the x-axis in seconds and acceleration on the y-axis in meters per second squared. And so the car starts moving with positive acceleration, but once it hits its peak at around 1.6 seconds, it begins moving with negative acceleration. And we solve for this by doing acceleration equals v final minus v initial over t final minus t initial for both the positive and negative acceleration. So now we have our energy bars. So the initial is at 0 meters. Work goes into the car, and the starting line represents the 0 reference point because the car is not yet in motion. And then when the car is traveling, it has kinetic energy, and work is going out of the car. And to solve for that, we have work equals kinetic energy. So we have the equation 1/2 mv squared is for kinetic energy. So again, we plug in our values, we plug in our mass and our velocity, and we solve for that, and we get our work is 0.0486 joules. And because we have work equals KE, since the work equals that also equals the kinetic energy. So our kinetic energy is the exact same. And then the final is at 1.6 meters, and there's nothing because it's stopped. And there's no height, so it's not potential energy either. And so our car came to a stop when our rubber band wheels rubbed against the tile floor, causing friction and heat to be produced. And this relates to the law of conservation of energy. So overall, our car was stopped after 1.6 meters because all the work had been used in the system. Now we have the forces and free body diagram. So here is the free body diagram of our Mousetrap car. And we set it up because there is gravity and normal force and a friction force acting upon the car. And the normal force is just the mass because it is equal to the force of gravity. So it's equivalent of the weight. So the calculations for both of those are the same, which was our mass was 248.9 grams. So we divided that by 1,000. And then multiplied that by 10 to get our newtons, so our force, our normal force, and our force of gravity. And to calculate the friction force, we used force equals ma, where F is the force, m is the mass, and a is the acceleration. So this equation also demonstrates Newton's second law of motion. So then you just plug in your values, and then we got our friction force, or F net force, was 0.15 newtons. So lastly, we calculated the coefficient of friction by using the fun equation, which is friction force equals mu normal force. So then again, we just substitute in our values and solve, and we got our friction coefficient would be mu equals 0.06, and that is how you solve for that.
Now we're going to talk about momentum. P equals mv, momentum equals mass times velocity. P equals 0.2489 times 0.625, which equals 0.16 watts. Right. Momentum is the force, speed of movement of a physical object or course of events. It is measured by the product of a moving body's mass and velocity. The more mass an object has, the greater the momentum will measure to be. If the object does not have mass, it does not have momentum. Lastly, it is harder to stop and requires more force to stop an object with greater momentum.
Next, we're talking about the power and impulse. And so power is defined as the rate at which energy is transferred. And the equation for that is power equals work over change in time. And so work is equal to FAX. So we first solve for that by plugging in our force, which is 0.15 times 1.6, which was our distance that our car traveled. And that equaled 0.24. So then we substitute that into the power equation. So we had power equals the work, which is 0.24 over the change in time, which was 3.2 seconds. So by calculating that, we got our power was 0.07 watts. Excuse me, our power was 0.075 watts. And by definition, impulse is the change of momentum or the force acting during a period of time. And the equation for that is impulse equals F delta T, which is impulse equals force times change in time. And so again, we just substituted in our values, which was our force was 0.15 times 3.2, which was our change in time. So our impulse equals 0.48 kg meters per second. And that is how you solve for power and impulse.